Okay, can everybody hear me? Would you say yes? Okay, good. Thank you. So I'm gonna wait about 1 or 2 minutes and then start. Okay, so let's get started. So this is gonna be the last part of, this this course on logic, and the last part is going to be about decidable theories. So we will consider, we'll define the notion of theories, and then for first order logic, and then we will show that in some cases, these theories have an algorithm. So we can design an algorithm, which is typically very inefficient, but basically we can come up with an algorithm that can decide whether some first order logic sentence follows from the theory or not. So some theories we're gonna consider, some of the theories will be about something called unbounded dense linear order, and some other theories will be something which is a bit more familiar, which is called Pressburg arithmetic. This is number theory with only addition without multiplication. Okay. So to talk about this decidability, we will have to formally define the notion of a theory. And then, okay, so we will have to first define the notion of a theory. And when we define this, we will make an assumption that we will fix this as signature sigma, okay? Signature sigma is fixed. And then when we talk about a theory, we are really talking about a theory over the given signature sigma, okay? And theory is nothing but a set of first order sentences over this signature sigma that is closed on the semantic entailment, which means that, so this T, or this strange T is, if you just expand this definition, it's gonna consist of a bunch of first order sentences like F1, F2, and so on. Typically, this theory is infinite. And the theory, in order for this set of first order sentence to be a theory, it has to satisfy this condition, and then the left-hand side of this condition said, if there is a sentence F such that follows from the theory T semantically, so then that sentence F should belong to T. And the condition here that I underlined, if you forgot about what the condition is, this condition means for all sigma structure A, if A satisfies in this T, which means that A satisfies all the sentences in T, then A should also satisfy F. So this intuitively means, the first order sentence F follows from this set of sentences in T. Okay? And then in order for T to be a theory, it has to be closed under this semantic entailment in the sense of the one that you see on the slide. And but there are certain kind of theory which is complete, which satisfies so-called completeness condition. So this completeness really means this is a theory which is as big as possible without really being inconsistent. Okay. So a theory is called complete if for any sentence F, either this F belong to the theory T or its negation is belong to the theory T. So we're gonna see some examples of this complete theory, but implicitly what this definition says is that for, so what this one said, this one implicitly said there may be some theory T, and some sentence F such that although T is a theory, F is not in T, and the negation of F, so both of them are first order sentences, they are not in T. Okay? So this is possible in general, but complete theory is the one where this is not possible. So for the theory is complete, that means either sentence F belong to the theory or negation of F belong to the theory. Maybe at the end of the lecture on Wednesday, I'm gonna mention about the importance of completeness. So really in the area called model theory, they are studying model, which means that they are studying something like this first order structure A. That's what they are studying. And these first order structures are, in a sense, what you normally study in mathematics. But they study it from the first order logic perspective. Then really what they take, studying this sigma structure A is in a sense equivalent to studying so-called complete theory. I'm going to mention about this later, and they form topological space using complete theories and so on. Okay, so that what you need to know here is the notion of theory, which is a set of first order sentences closed under entailment, semantic entailment, and a theory is called complete if for every sentence, first order sentence F, either that sentence or its negation should belong to the theory. Okay. And then there are two recipes for generating theories. First is more semantic, the second is more syntactic. The semantic approach is we pick a structure A, okay? And so this A is a particular structure, and then we collect all the first order sentences that is true under that structure. Okay. So that's what this is doing. We call theory of A. So we pick a structure A, and then we collect all the sentences that's true under A, and that forms a theory. And this is called the theory of a structure A. So this is more semantic because we are starting from the semantic notion, which is a structure. The second one is more syntactic. So in this case, we are collecting a set of axioms. So a set of this S is a set of first order sentences. It can be infinite, it can be finite, it doesn't matter. We collect a set of axioms, a set of sentences, they are called axioms. And then we define a theory T by collecting all the sentence F that is followed from S semantically, okay? So we collect all F that satisfies this condition, which said this set of sentences S entails the sentence F. Okay. So we're gonna see an example of the second and the first and the second, and then the typical example of this set of axioms that you maybe learned about it before is that the set of axioms for group theory. Groups should have a unit and composition operator, which is associative, and so on. And they are typically axiomatized using a set of the finite collection of first order sentences. And then if you generate a theory using this second recipe, that's going to be a theory for group theory. Okay, so now here are some exercises I want you to solve. So here are three exercises. I will give you 5 minutes to think about these three exercises. The first exercise is, first prove that both recipe always give theories. Okay, so theory is not just a set of sentences. It's a set of sentences closed under this semantic entailment. So prove that whenever we define this theory using first recipe or second recipe, they are all both closed under semantic entailment. The second question is, actually one of the recipe always give rise to a complete theory. So pick one which give rise to a complete theory and find some argument, come up with an argument why that is the case. The third, try to come up with an example of an incomplete theory. Okay. So I'll give you 5 minutes to solve, for you to solve these 3 questions. Okay, so let me answer these questions. So for the second, let me just use this extra note. Okay. Space here. Okay. So, for the first exercise, both of them are theories. The proof is really simple. So, to show that, this TH of A is a theory. Why that is the case? So, why? And to see this, suppose that if we have some sentence F such that this TH of A implies the first of the sentence F. But the definition of this semantic entailment is any structure satisfying on the left-hand side, satisfying this, that also has to satisfy the first of the sentence F. But we know because the way we generate this theory of A, we just generate this theory of A by collecting all the sentences true under A. So we know that A satisfies theory of A, thus A will also satisfy F, which means that F should be a member of theory of A. Okay. So, and then for the second, we said this T, which is generated from set of axioms, let's call it S, is a theory. And why that is the case? If we said this T of S entails F, so then what we know, what this say is for every structure A satisfies T of S implies the same structure which satisfies F. Now, in particular, now what we have to show is that for we have to show this guy, which means for any A satisfies S implies the same A satisfies F. So this is what we have to prove. But if A satisfies S, so then that implies A satisfies T of S. That's because T of S is constructed by collecting all the sentences that's entailed from S. So this is true by constructions of T of S. So then, now by assumptions, this one implies A is F by assumption. So we show that A entails S, A satisfies every formula in S implies A satisfies the given formula F. So that's what we have to show here. So this means that this F is now belong to T of S. So that shows that both of them are theory. And then for the second question, the complete theory is TH of A. If the set of sentences, so typically we consider a set of sentences which is satisfiable, but the definition does not exclude this unsatisfiable case, because if it's unsatisfiable, this theory T will be it will consist of all the formulas. Okay, so as Chang Hyun said, typical examples S is satisfiable, but our definition so far doesn't really exclude this. And then actually there's a terminology which is called consistent theory, which means that the set of the theory is satisfiable. It doesn't contain bottom. Theory doesn't contain false. That's called consistent theory. But that's a concept we don't really talk about here. Okay. Right. For the complete theory is TH of A. And in general case, that's because and then why that's the case? If you're given a sentence F, so then we know that formula that is structure A will either satisfy F or A is not going to satisfy F. This is with respect to a specific structure A, it either satisfies F or it doesn't satisfy F. But for the second case, if A doesn't satisfy F, that means A will satisfy negation of F. So if we have the first case, this means that F should belong to the theory of A. And the second case, negation of F should belong to theory of A. So although this is just maybe very bad analogy, this theory of A in the computer science term can be understood as A is a bit like implementations. Theory of A is an abstraction that's achieved by the implementation. In this context, we only care about first of the sentence. So this theory of A is something which means that A talk means like everything that A talk about first of the sentence, they are all collected in the theory of A. And yeah, but that's what some intuitions about this. More mathematically, theory of A induces some equivalence relation on the structures. But anyhow, this is what the first order logic say about this structure A. So that's what this theory of A is. For the third example, the example is a group theory. But so in the group theory structure, sigma is usually have a unit and binary operations, and then this set of sentences, they are having some sentence which talk about group axioms. For instance, it has an axioms like for X, for Y, and for Z. Talk about associativity. X, Y, Z, same as X and Y and Z, and so on. So it has a usual action. I mean, if you don't know the group action, doesn't really matter. So there are something called group theory, and then that group theory have a bunch of axioms, and then this axiom is incomplete. Why that's the case? I mean, then there are some first of the sentence which say this operation is commutative. So this is a specific sentence, and S doesn't imply in this F commutative, doesn't imply F of C. Also, Fs doesn't imply negation of F of C. And intuitively, that's because there are groups whose operation is commutative. There are also groups whose operation is not commutative. So this is not the case. So if you, again, don't understand this example, it doesn't really matter. What I'm pointing out is that if we follow the second recipe, typically we end up with an incomplete theory. But there are some cases where we get a complete theory. Okay, so let's move to the next. So here are some examples of two examples we're gonna look at very closely. The first example is the theory generated by the first recipe. The second is theory generated by the second recipe. So the first theory is called the theory of linear arithmetic over rational. So we're gonna use this letter which is called T, subscript LAR. L means linear arithmetic over rational. Okay. And then the signature in this case is going to, that we're gonna use as a constant symbol 1, plus functions, the binary operation function symbol plus, and then there are infinitely many unary operations, which is called C dot, for all rational number Q. Okay, so this is actually there's one more. And then there are one predicate symbol less than. Okay, so this is our signature. And then our structure is its underlying universe is set of rational numbers. 1 is interpreted as a rational number 1. Plus is interpreted as a usual plus operation. C dot is interpreted as, I mean, this is really the unary operation. It's a constant multiplication operation. Less than is interpreted as a less than. So they have an interpretation that you expect. So this is the specific signature structure A. I mean, the kind of what you expected structure. And then we are thinking about the theory which is generated by the structure. In other words, we are collecting all the sentences that is true under theory A. In other words, we are really collecting all the first order logic sentences that are true over the rational numbers that you normally know, I mean, the usual rational numbers. And actually, this theory is quite powerful. It can be used to talk about various things from linear algebra, because this is really about linear arithmetic. So one thing that we can say, with the kind of sentence we can form here, and then we want kind of things we can check here is that given a matrix A, so this is a matrix, X is a vector, B is a vector, then we can write this matrix multiplication AX is smaller than equal to B using the, as a first order logic sentence. And then we can also set using first order logic sentence, this matrix inequality has a solution. Well, does not have a solution. So that's the kind of things we can express. Another thing we can express using this signature is any solution of AX less than B is also a solution of CX less than D. That also can be expressed in this using the signature over this linear arithmetic over rationals. And then the truth about the sentence can be checked by using this theory over linear arithmetic over rationals. Okay. So that's a first theory. And the second theory we're going to consider is something based on axioms. It's following the second recipe. And that's a theory over the following signature. This signature is a bit weird if you see it first. It doesn't have any constant symbol. It doesn't have any function symbol. It only have two predicate symbol, less than and equality. And then equality, is really have the usual meaning. So two things are equal if they are really equal. So sometimes this is called first order logic with equality. And then for this theory, it formalizes properties about, this order. And it says that this less than is a so-called unbounded dense linear order. Okay. So let's look at, and it's formalized by 5 axioms that you see on the screen. Let's just start to look at the second axiom first. Second axiom says for every x, y, z, x is less than y is less than z. That implies x is less than z. So this is sometimes called transitivity. So means, and the third one, which say given any xy, they are in some relationship, either they are equal or x is less than y or y is less than x. So this is sometimes called the linear order or sometimes called totality. And then the first condition is sometimes it's called, actually put sometimes called two properties, two properties together. One is called irreflexivity. If x is less than y and x and y are different. So that's what the first part is to say. And the second one is called asymmetry, which says x is less than y, then y is not less than x. So this is irreflexivity. And asymmetry. And the third, and then the fourth and the fifth properties are, the fifth properties are about unboundedness. So you say that for any x, you can find something smaller and also you can find something larger. So you can find something smaller y, we can find something larger z. So that's why this theory is called unbounded. And then the F1 to F3, they are about this linear order. So it's about F1 to F3. Unbounded is formalized by F5. Dense is formalized F4. So dense means whenever xa is less than y, you can always find something which goes in the middle. So z goes in the between x and y. That's always possible. So structure that satisfies all these formula is a set of rational numbers because it doesn't have any in the smallest or largest number and then less than relationship satisfy all of these property. Something which doesn't satisfy number 4 but satisfy all the rest is a set of integers, because for set of integers you can't, if you pick say 3 and 4, then you can't find anything in between. So it doesn't satisfy this dense property, but all the rest is satisfies this. So this is called a theory of unbounded dense linear order, and that plays, that appears quite often in mathematics and in also computer science in automated theorem proving. Okay, so these are the two examples, the theory of arithmetic over the rationals, and then the theory of unbounded dense linear order. So we're gonna use TLAR for the first, TUDLO for the second. Now, here's an important property that we will care about in this lecture, which is a decidability. And we say that a theory is decidable if there is an algorithm that takes formulas, first order sentence F, and then returns that whether that formula F belongs to the theory or not. Okay. Note that although the theory is semantically means a set of first order sentences, if you look at the previous slide, we didn't really write down the set of this first order, infinitely many first order sentences explicitly. They are all specified implicitly by either first recipe or the second recipe. So decidability means that it makes sense because we don't really need to spend entire time just to write down this infinite set of T. Okay, and the theory T is called decidable if there's an algorithm which decides the membership of a first order sentence to the theory. And now that then here are two questions. Maybe I will give you 30 seconds to think about. We looked at this theory of linear arithmetic over rational numbers, and then also a theory of unbounded dense linear order. The question is, do you think they are decidable or not? So I will give you, I don't expect you to find the right answer, but I give you like 30 seconds to think about. Okay, it turns out both theories are decidable. So there are algorithms that can check the membership of a given sentence F to the theory, this TLAR. Also, there's another algorithm that takes the formula F, a sentence F, and they can say whether that sentence belongs to the theory TUDLO or not. And other interesting bit is that although the first theory generated by axiom is not necessarily complete, this turned out to be complete as well. This kind of things do not happen often, but that's the case. And then actually, what I'm gonna show you, which is the decidability by quantifier elimination, can also be used to show the completeness of this TUDLO. So which means that this is a very, very special theory. Okay, so then the proof or algorithm that we're gonna get for this both cases is gonna be based on so-called quantifier elimination. And here's a definition of quantifier elimination. We say that a theory admits a quantifier elimination if the following property is true. So the properties say for any formula exists x dot f, where f is quantifier free, but this entire thing, it has an existential quantification. Also, this exists x dot f do not have to be closed. So it may have free variables and typically have free variables. Okay, so in order for a theory to be quantifier free, the following condition has to be true. Any exists x dot x, I mean the exists xf, there exists a quantifier free formula G such that this exists xf and G are equivalent under the theory A. So what does this mean? This means that for any structure A that satisfies T, for maybe just write it more explicitly, it's easier. So for structure A such that A satisfies T, then as far as A is concerned, this exists f x dot f and G are say the same thing. A satisfy exists x dot f if and only if A satisfies G. Okay. So maybe if a structure doesn't satisfy T, they may be different. But if we focus on the structure that satisfies T, or that satisfies the theory, exists x dot f and G are say the same thing. And this process is called quantifier elimination. That's because the formula G doesn't have any quantifier. And we say a theory T has a quantifier elimination procedure if there's an algorithm that take exists x dot f and generate G. Okay, so we can algorithmically compute G from a given exists x dot f. So that's what this quantifier elimination means, and then the quantifier elimination procedure means. Then here are some theorem which say if we have a quantifier elimination, then we can almost have this theory is decidable. So it say that theory T is decidable if we satisfy two conditions. The first, it should have it has a quantifier elimination procedure, so like the one that I described here. Second, it has a procedure for deciding the sentence F belong to T or not for the formula, the F, which is quantifier free and also sentence, which means that it's closed. So this F, we focus on the quantifier free. So it's much simpler formulas than the generous first order logic formula because it doesn't use any quantifier. Second, it has to be sentence, which means that it doesn't have any free variables. Okay, so now here's an exercise I want you to think about. The exercise is to prove the theorem. Okay. So the theorem doesn't claim a theory T has a quantifier elimination. It just said if T has a quantifier elimination procedure, and then it also has a procedure for checking membership for quantifier-free sentences, then the theory is decidable, and try to prove this theorem. Yeah, okay, so actually the theorem is quite easy to prove, although the consequence is quite important. So what we do, we have, if we given a first order, we want to show it's decidable. So then what we have to do is we have to construct an algorithm. So that algorithm takes F which is first order sentence. And then the first step of the algorithm is we transform f to maybe rectified pre-next normal form. So then we know that this f and f prime, they are equivalent. So they logically, they mean exactly the same thing. And then now this f prime is a rectified pre-next normal form, which means that it has the form for all x1 up to for xn. And then it has, what is it? It has this matrix f prime star. Maybe using this extra board is needed. Okay. So, okay. So then we convert it to the pre-next normal form. Now sorry to moving from one slide to the next, but the next step, what should we do? We view this for x1 and xn. We write it as an existential quantification. So then it's the same as exist x1 negation, right? Actually, x2 xn and negation of f prime star. So this is the same as equivalent to this for x1 xn up to f prime star. And then we apply the quantifier elimination from the inside out. So if you apply the quantifier elimination here, then that's going to produce, gn. Now, if you do the, say, exist xn minus 1, quantifier elimination to this guy, we get gn minus 1, and so on. So we get all the way to g1 with the negation. So, and then this g1 with negation, this is a quantifier free. And another thing we know is that g1 with negation is equivalent to f prime that we started with, which is also equivalent to original formula f. Okay, so we start with the f, we apply the user transformation and transform the rectified pre-next normal form, and then we using this simple tricks with the negations using De Morgan's, and then we apply this quantify elimination procedures from inside out, and we get this negation of G1, which is equivalent to the original formula, but it's a quantifier free. So that's an important part about this. So now because this quantify, so one thing I didn't say about this quantify elimination is when it does quantify elimination, it doesn't introduce any new free variable at all. Okay. So we start with this entire thing. It was a sentence. Okay. So this was a sentence, which means it was a clause. So this negation of F1, this will also be a sentence. So it doesn't have any free variable and also quantifier free. So then we can, by the second assumption, we can apply the procedures, assume the procedure. To check whether this negation G1 belong to T or not. So if negation G1 belong to T, then we can say this original F belong to T. If it doesn't belong to T, we can say F, no, F does not belong to T. And we can do this because F is equivalent to negation of G1 also under T. So under T, they are equivalent. Also, T is a theory. So because of these two properties, after these transformations, if negation of G1 belongs to T, then we can conclude F belongs to T. Otherwise, we can conclude that F does not belong to T. So that's how you can derive an algorithm from, we can prove the theorem. Now, then the question becomes how we can do this quantifier elimination. So that's actually the core part, or most difficult part of the proving some theory is decidable, or designing very generic algorithm for a particular theory. So here's what we're gonna do. So we will first consider this theory of unbounded dense linear order, and we're gonna show it's decidable. So then following the recipe in the previous theorem, we have to do two things. The two things is that we have to come up with a quantifier elimination procedure, and also we have to come up with a procedure for deciding the membership of quantifier-free sentences to the theory. Okay. So that's how we're gonna prove this. So we have to quantify elimination procedure and decision procedure for quantifier-free sentences. So here's a exercise I want you to do. Think about how you can come up with a design a decision procedure for quantifier-free sentences for this particular theory. And some hints that I can give you is that this theory is over signature sigma, which doesn't contain any constant function symbol or constant or function symbol. It only contains less than and then equality. And then equality has the usual meaning. Okay. So I will give you 1 minute to think about this, which means that it's actually quite easy. So the answer for this question is quite easy. Okay, so the answer is quite easy. So what you can do is that if you look at the quantifier-free sentences over the signature sigma, okay, because we don't have any constant, we don't have any function symbols, the only atomic predicates that can appear in the quantifier-free sentences are just true and false. Okay, that's all. That's it. Because we can't use variable because it's a sentence, and then there are no constant, no function symbols. So it's just Boolean combination of a true and false, which means that you can just evaluate the value of this quantifier-free sentence just using truth table, and that will give you either true or false. So in this case, the formula F can easily prove that this is equivalent to either true or this formula F is equivalent to false by evaluation. So, right, so this because of, F is equivalent true or false, if we get the first case, then we can conclude that this is, this belongs to this theory, T of UDLO. If it's a second case, we can conclude that this doesn't belong to the theory. Okay. That's because this theory should be closed on the semantic entailment. Any theory will contain true, because true is always implied by semantic entailment. So if because also this F is equivalent to true, then that means F also, everything equivalent to true should also belong to the theory. So F should belong to here. And this theory, I mean, it doesn't really contain false. I mean, it's a consistent theory, so it doesn't contain false. So it's anything equivalent to false shouldn't be there. So you just evaluate this, and if it's true, say this it's in the theory, false is not the theory. So that's how you can design an algorithm here. Now for difficult part is proving the quantifier elimination procedure. So here I'm gonna give you some hints and then give you 5 minutes to think about this. So here are the hints. So what we have to do is that we can assume we are given existentially quantified formula exists x dot f, where f is quantifier free. And then we have to get rid of this existential quantification. In other words, we have to come up with a formula G, in this case, G prime, which is equivalent to exists xf. Okay. Now how you do it? And then we're gonna do it in 2 steps. The first step is we will change because f is a quantifier-free formula. We can massage this quantifier-free formula. We will change it such a way that this exists x dot f it becomes equivalent to a bit more complicated formula, but it's actually quite simple. I mean, it has a disjunction and conjunctions, but the part which have an existential quantification is really simple. It's just that it exists x gi. Gi is just a conjunction of the less than assert predicates, but where x appears in one of the side. So the first condition said gi is of the form x is perhaps like a y1 and x is y2, and maybe it also have a lower bound c1 x and g2 x, maybe g3. So we have to first show that given any formula exists xf, we can transform it into formula of this form. And then once we transform a formula of this form, then we can focus on removing existential quantification for this specific form. So this, I mean, this things is x dot. There's a simpler formula like here, and we focus on removing existential quantification for this simple kind of formula that can be doable. So that's our step 2. So think about how to solve this, how to come up with a quantify elimination procedure for this TUDLO by following these 2 steps. I will give you 5 minutes to think about this. Okay, so let me explain how it works. Right, maybe just clear a little bit. Okay, so then for step 1, which is a transforming, the transform exists x dot f into for some disjunctions, and then xgi and hi. So how to do this? So we do it by going through the multiple steps. The first, we get rid of negation from f using De Morgan. So by using De Morgan's law, we can move negation from outside to the all the way to the base case, and then some tricks or equivalences following equivalences in the under the theory. Under theory T, U, O. What are the equivalence? Equivalence say if we have a negation of x less than y, we actually don't use a more generic term. So say y less than z, and this one is under T. It's an equivalent. So under theory T, it's equivalent to saying y is equal to z or y is greater than z. Okay, so that's because, right, so y is equal to z or y is greater than z. I mean, because of one of the axioms in this theory T. And another things is DLO. If y is not equal to z, that is equivalent to y is less than z, or y. I think maybe just using one of them is better. In z is less than y, z is less than y. So we can do, if we use De Morgan's, and then these equivalences, so then we can get rid of negation. We can put negation all from outside all the way to the base case, and then in the base case, you can get rid of this by using De Morgan's law. So after this, the negation is gone. Then we do that with, and we transform the resulting f prime into DNF, into a DNF formula. F double prime. Okay. So this DNF formula, let's just make it more explicit. It's gonna be have the form F double prime. Maybe using, it has some clause C1 or clause C2 and clause CM. So this will have this form like this, and each of the clause will be a conjunction of either equality or less than between variables. Okay, so then what should we do? We move negate. So then what we have in the resulting formula, then we put existential quantification from outside of F double prime to over each of the CI. So we have this exist F double prime. It gets transformed into exist X C1 or exist X C2 X CN. And this is okay because existential quantification, if you put, these two formulas are equivalent, so you can move existential quantifications. We can kind of distribute existential quantification over all these disjunctions. Okay, so now we get quite close to the formula that we are talking about. So this is the formula that we are talking about, where we have a disjunction outside and existential quantification. And we have a disjunction outside and existential quantification. Now we look at each of these CI. Okay. So we look at exist X and CI. And CI will consist of the conjunctions of the form of non-negated literals like L1, L2, and LM, ML, L, M, Z, LN. And then some of them, one contain X. And for the rest, X appears. Okay, so then what we can do is we can take this part, which doesn't contain X, outside of existential quantification. And why this is okay? That's okay because if we have exist X, some formula F and G is equivalent to, okay, this is equivalent to exist X, F, and G if X doesn't appear in G. So we can take this part out, and then the outcome is, this formula will get transformed into exist X, where we have something like a GI and what I call HI. Now we have to do one last step. One last step is now if I look at GI, that will contain, GI will be of the form, it will have something involving X. On the left-hand side of this less than relation, something involving X on the right-hand side of less than relation, and then something which involving X in the equality, left-hand side, equality on the right-hand side. Okay. So in this, we do a few of it processing. So this is what appears in GI. We do a few processing where if you see, for instance, X less than X, this will never be true. Because of irreflexivity axioms. In that case, we just replace everything to false. And then if X is equal to X, we just drop it because X is always equal to X, so it doesn't have any information. The third case is if X is equal to Y, where Y is different from X, then in that case, we replace the exist X GI by GI where X is replaced by Y. Okay. Because X should be equal to Y, so then we can just replace this. So these are the three pre-processing. So then after this, we can assume that if we see X less than, this one always should be some variable Y which is different from X. And then if we see another less than, this part also should be something different from X. And then we don't have any equality at all. So because of this pre-processing. So now after all this, although it looks complicated, this is actually quite simple manipulation. First, we move negation from outside. Okay, maybe just so we first remove the negation from outside, and then second, we do the DNF transformations, and the third, we just distribute existential quantification like this. And fourth, we took out, for each of these existentially quantified part, we took out X-free part from inside of existential quantification to the outside. And then finally, we do the post-processing to get rid of certain formulas like X less than X, X equal to X, X equal to Y. And if we do all of this, then we end up with a formula that's described in the screen. So we have a disjunction outside, and then each of the disjuncts, we have existentially quantified part, and something which doesn't involve X at all, which is written as an HI. And GI will always be a conjunction of X less than Y and Y less than X. Okay. Although complicated, actually, conceptually, it's not very difficult. And then now the more difficult part is the number 2. Okay. So for the number 2, actually, we go to the next slide. So for number 2, I mean, we have to do a bit more work. So to do this work, we kind of notice some patterns of G. So here the pattern is, after all these transformations, G will be reasonably simple. G will have, two parts essentially. The one part is really about the lower bound of X. So this is C. And the part that you see on the screen is about the lower bound. And then the remaining part will be about an upper bound of X. Okay, so that's the formula that we get in G. So G is this formula, which is really coming from here. So now what should we do? So then we do case analysis. The first case is if we don't have any lower bound or we don't have any upper bound. In other words, this blue part, suppose we don't have any blue part, then it is always possible to find X that is less than U1 up to UN, because we are talking about unbounded dense linear order. So the last axioms say that it is always possible to find something arbitrarily small. So if M is equal to 0, we can replace this exists X with true. Similarly, if we don't have any upper bound, so if N is equal to 0, which means that this red part doesn't exist, then by the same reason, we can just replace exists XF to be true, because we can find arbitrarily large elements in this, according to this dense linear, the theory of dense linear, right? Yeah, so the unbounded dense linear order. So in either of these cases, our algorithm can replace this exists X dot, actually it's not F, this has to be G, X dot G by true. So now for more complicated cases, when this M is not 0, N is not 0, in that case, we can replace this exists XF essentially by saying maximum of L1 up to Lm should be smaller than minimum of U1 up to UN. So this complicated relationship between Li and Uj is a way to say the largest lower bound should be smaller than smallest upper bound. Any lower bound should be smaller than the upper bounds. Then that's exactly the same thing as what I just told you. Now, if you do this, then you can see that X disappeared completely. And why this equivalence is okay? I mean, this equivalence is okay. That's because one of the axioms in T UDLO is about the dense property, which say if you pick any two element, one is smaller than the other, you can always find something in between. So if the condition on on the right-hand side of this equivalence, if this condition is true, this intuitively means max of Li, Lm, is smaller than minimum of upper bound, Un. So then by dense linear order, because something is smaller than some other things, we can find something dense property. We can always find something in between. So that's why these two things are equal. I mean, I give this is more like an informal explanation, but you can formally convert this informal argument into the formal proof here. Formal arguments to show that these two things are equivalent. So just to sum up, we have a quantify elimination in this case. Quantify elimination first take exist x dot xf into some simplified formula where existential quantification is only over conjunction of some with some less than relationship involving x. And then because it's this less conjunction of less than involving x can be grouped into lower bound and upper bound. And we can essentially encode this entire exist, here is G, exists x dot G by the largest lower bound is smaller than greatest, no, largest lower bound is smaller than least upper bound. And that doesn't involve this quantify the variable x at all. So these are the two steps for the doing quantify elimination. So in putting all these together, that gives us, that gives us the decidability of the theory of unbounded dense linear order. So decidability, we have a quantify elimination procedure, and I also have a procedure for checking the decision procedure for quantify free sentences. And the other example that we see in the lecture is about this theory of linear arithmetic over the rationals. That is also decidable by exactly the same reason, or almost the same reason. The proof about this appears in the notes, lecture note that you can see on the KLMS. And then proof we follow exactly the same pattern. The first, it consists of two steps. The quantify elimination for this theory have two steps. First step number one is almost the same as that you see before. Step number two is almost the same. Essentially say the lower bound, the largest element in the lower bound should be smaller than smallest element in the upper bound. Okay, so I encourage you to have a look at this. So that's it for today. And then on Wednesday, we're gonna move on to something called the Pressburger arithmetic. And then we will discuss about the decidability of Pressburger arithmetic using quantify elimination. So I'm gonna stay here for about 5 more minutes. So if you have any questions, you can ask me. Okay, thank you very much.